Welcome back to my series of ACE, the Technical Pilot Interview Summaries. In this installment, I'm going to be covering chapters 6 and 7. For anyone that's been following this series, I apologize for the delay in uploading this video. I've been quite busy. As always, make sure to download the PDFs from the link in the video description. And with all that said, let's get started. The pressure flight instruments are airspeed, altimeter, VSI, and Mach meter. The airspeed indicator suffers from instrument, pressure, density, compressibility, maneuver, and blockage errors. On the speed tape, the VMO or MMO is shown as a red and black striped portion. Mach number is a function of temperature and true airspeed. Aircraft flight instruments, however, operate using pressure differential to compute Mach number, not temperature. What this means is that a Mach meter is essentially an airspeed indicator with an integrated altimeter element. The Mach meter does not suffer from density or temperature errors for this reason. The instrument or pressure errors are negligible. Modern Mach meters use the air data computer for its inputs. A static line blockage at a constant altitude does not affect the airspeed indicator. With a blocked static port and in a descent, the airspeed indicator will overread due to the increased total pressure while static pressure stays constant. In a climb, it will underread. If the pitot tube is blocked, airspeed indicator will underread in a descent. It will overread in a climb due to the decrease in static pressure while total pressure stays constant. QNH leads to an indication of the aircraft's altitude above mean sea level. QFE leads to an indication of 0 feet if the aircraft is on the airfield surface. Altimeters are susceptible to instrument, pressure, time lag, barometric, temperature, and blockage errors. Please keep in mind that temperature errors can also be known as density errors. If there is a static line blockage, the altimeter will simply freeze at that altitude. If colder than ISA, the altimeter will indicate a higher altitude than the true altitude because the denser air column will be compressed. This is usually not corrected in aviation as it is easier to have everyone equally wrong. A servo-assisted altimeter is a more accurate variation that eliminates the frictions between the moving components of an aneroid barometer. These altimeters do not suffer from time lag error. An IVSI uses two spring-loaded weights between the instrument and the pointer, which use inertia to display a rough vertical speed change immediately following a change of altitude. This removes the lag error of a typical vertical speed indicator, which works by metering the instant rate of change of static pressure inside a capsule in comparison to the static pressure in the instrument case. The instrument case has a metered release valve and thus cannot react instantly. A downside of this system is that it will incorrectly indicate a climb when you roll into a high bank angle. It will also indicate a descent when you roll out of the turn. A static blockage will freeze the vertical speed indicator. Modern airplanes feed their pitot-static measurements into an air data computer. This computer can calculate the RAS, TAS, Mach number, total air temperature, vertical speed, and feeds all this data to servo-driven display instruments in the cockpit. The air data computer can also feed all the information it derives from pitot-static data into systems like the Autopilot, the flight director, the flight management system, the ground proximity warning system, nav aids, and more. Gyroscopic flight instruments are the heading indicator, the attitude indicator, and the turn coordinator. Gyroscopes measure the force exerted on its rotor body when its housing maneuvers, the housing being attached to the aircraft. The rotor is suspended in one or more frames called gimbals, which are at right angles to each other if viewed from atop the rotor. One gimbal is required for each axis upon which you wish to measure the instrument movement, accounting for the effect of precession. A gyroscope can have up to 3 planes of freedoms, each of these represented by an axis and a gimbal. A gyroscope's rigidity is a factor of the vacuum or the electric force driving it. Poor rigidity leads to gyroscopic wander, which is a movement of the spin axis away from its fixed position. This can lead to an inaccurate instrument reading. Apparent wander is a different phenomenon, and it is caused by the rotation of the Earth. Apparent wander is inescapable. To correct for apparent wander, gyroscopic instruments must be recalibrated every 15 minutes or so, or a correction must be applied with a latitude nut. Transport wander is better explained with an example. An aircraft takes off from Mexico with its directional indicator gyro aligned with true north. As the aircraft flies towards Spain, the change of longitude causes an error. This error is not present in north to south bound flights. Total wander is a sum of transport wander and apparent wander. The artificial horizon has a gyroscope oriented with a vertical spin axis. It has 3 planes of freedom, spin axis plus 2 gimbal axes. The gyroscope stays aligned with the rotor parallel to the surface. Gimbals measure pitch and roll respectively. There are turning, acceleration, and spin axis wander. Electrically driven artificial horizons are more rigid, as they rotate the rotor at about twice the RPMs of a vacuum counterpart. They have around 85 degrees of pitch indication either way from the horizon and have an unlimited roll indication. Turn coordinators have 2 degrees of freedom: rotor spin axis and yaw axis. Thus, measuring rotation about the fore to aft axis of the plane, as well as the aircraft's yaw through its vertical axis. A turn coordinator has its gyroscope aligned with the wings. This is the lateral axis. If the compass points to the east of true north, variation is east, also known as positive variation. This can be remembered using the following: variation east, magnetic least. Compasses must be reswung, calibrated, when there is a change in the electrical equipment, a large change in latitude, or some other less common incidents such as a magnetic storm. The remote indicating compass, or RMI, is a combination of a directional indicator and a compass. It includes a gyroscope which can be slaved to the magnetic detector unit. It's essentially a self-correcting gyroscope. Advanced flight instruments. The EFIS is a fully integrated navigation system which uses digital displays for EADI, Electronic Attitude Directional Indicator, and EHSI, Electronic Horizontal Situation Indicator. Other parts of this system are the EFIS controls panels and symbol generators. These systems display the same info in a clearer and more versatile manner, bringing together additional data from different sources to present the pilot with the best navigation information possible. The EADI display often includes the following information: attitude information, including the turn and slip, from the inertial system, flight director command bars, pitch limit indicators, as well as a rising runway indicator. The EADI also includes speed tape with trends, as well as a Mach and ground speed display, LNAV and VNAV deviation indicators, altitude and radar altitude indicators with minimums bugs, autopilot modes including auto thrust, pitch mode, roll mode, and autopilot status. Rising runway appearance is type specific, but often begins at 200 feet above ground level. When at 0 feet above ground level, the runway symbol will be in connection with the aircraft marker, not with the horizon. The EHSI has 7 display modes: full VOR/ILS, full nav, expanded VOR/ILS, expanded nav, map mode, CTR map mode, and plan view. In all expanded and map modes, the system is also capable of displaying weather radar information. The electronic flight instrument system color coding is as follows. Green means active or selected mode, or changing conditions. White means present situation and scales. Magenta means command information and also turbulence if the radar display is active. Cyan means non-active background information. Red means warning. Yellow means caution. Now let's move on to radio communication systems. VHF is used for short-range transmissions using line-of-sight propagation. Range is affected by the transmitter power, the frequency, obstructions, as well as fading. The line of sight of VHF communications can be calculated using 1.25 times the square root of the height of the transmitter plus 1.25 times the square root of the height of the receiver. These heights should be measured in feet above mean sea level. The previous video that I made in this series discusses this in greater detail. I recommend you watch all of these in series. High frequency or HF transmissions are used for long distance communications between two specific points. It uses predictable propagation paths, often refracted off the Earth's ionosphere over large distances. The pilot will choose frequencies within this band of 2 to 22 MHz, depending on the distance to its target receiver. Higher frequencies give a greater range. In all cases, HF can be received at a station 2,000 nautical miles away, but not one 500 nautical miles away at a given frequency, due to the propagation path. At night, half of the daytime frequency produces the same range due to the higher location of the nightly ionosphere, which is the E layer, versus the daily ionosphere, which is the D layer. High frequency range is also affected by transmitter power, frequency, time of day, season, location, or ionospheric disturbances. Let's talk about avoidance systems. TCAS stands for Traffic Collision Avoidance System. It provides maneuvering information to aircraft with conflicting flight paths. It uses the secondary surveillance radar, aka transponders, and is dependent of ground stations. Correction, it's independent of ground stations. TCAS 2 provides avoidance information restricted to vertical separation. TCAS 4 gives 3-dimensional resolution advisories, but is likely outshone by the ADS-B system, which is more capable. TCAS interrogates SSR transponders of nearby aircraft and plots their positions and relative velocities. Directional antennas on the aircraft will find the position and transmission time delay and will find the distance. As of January 2020, common TCAS systems only provide avoidance instructions in the vertical plane. Initially, traffic advisories are generated, but these may become collision threats, after which they are designated as resolution advisories. In this case, a command, in the form of a vertical speed to be flown, is generated so that the pilot may follow this and avoid the collision. Resolution advisories are more important than ATC clearances, but TCAS use is limited to traffic advisories in dense traffic areas. Resolution advisory descent instructions are restricted below 1,000 feet, and all resolution advisories are inhibited below 500 feet. Traffic advisories are restricted below 400 feet. TCAS can cope with mode A, C, and S transponders. If both aircraft are equipped with TCAS-2, the transponders will communicate with each other and coordinate an avoidance path using Mode S data link. ACAS, or Airborne Collision Avoidance System, is a European system. Ground Proximity Warning System, GPWS, is a system which takes into account the dangerous circumstances of excessive barometric rate of descent, excessive terrain closure, height loss after takeoff, incorrect gear or flap configuration before landing, below glide slope deviations, approach minima. GPWS uses various inputs to enforce its 6 modes, and works with 2 boundaries per mode, the crossing of which generate alerts. These boundaries are the initial alert boundary and the warning boundary. The warning boundary generates visual and oral alerts. The GPWS modes are referred to by their number. Number 1, excessive barometric rate of descent. Number 2, terrain closure. Number 3, sinking flight path after takeoff or go around. Number 4, gear or flap not selected. Number 5, ILS glide slope deviation. Number 6, approach minima. GPWS, or Enhanced Ground Proximity Warning System, is an enhanced version which can also display terrain mapping on the screens using onboard radar. The inputs to a GPWS system are barometric altitude, radar altitude, flap position, gear position, glide slope information, minima, and throttle position. If various warning boundaries are crossed, the higher priority one takes the display priority. The order of priorities are Mode 1, 2, 3, and 4, which generate a warning whoop, whoop, pull up. Then Mode 2, which generates a warning terrain, terrain. Then too low gear. This is the warning generated by Mode 4A. Then Mode 4B, too low flap. Then Mode 6, minima, minima. Then Mode 1, sink rate, sink rate. Then Mode 3, don't sink. Then Mode 5, glide slope, glide slope. The captain may override a GPWS warning considering the aircraft is 1,000 feet vertically and 1 kilometer horizontally clear of clouds with 8.5 kilometers of visibility, flying in daytime, and obviously not in danger. Once again, I instruct you to download the PDFs from the link in this video description, as they contain all the relevant information so you can follow along the PDF whilst watching the video. Now, modern aircraft use ADC detected changes in airspeed to calculate the presence of wind shear phenomena. These detections are fed through the ground proximity warning system to be displayed on the electronic attitude and directional indicator. A wind shear warning requires immediate go-around at full thrust with flight director directed pitch attitude. If this fails to provide a net positive climb, the aircraft should be pitched to eyebrow limit. Note: wind shear, GPWS, and TCAS are prioritized in the respective order. A flight management system, FMS, is an onboard, multi-purpose navigation, performance, and aircraft operations computer designed to provide virtual data and operational harmony between closed and open elements associated with a flight, from pre-engine start and takeoff to landing and engine shutdown. FMS has inputs from stored databases, pilot inputs via the control display unit, as well as other aircraft systems which automatically feed the FMS. LNAV and VNAV, which stand for lateral and vertical navigation respectively, are modes of the FMS, which can be selected as guidance in manual flying or can be selected to govern the autopilot and autothrottle systems. The flight management system contains company routes which may be amended by the flight crew. The autopilot stabilization capability is broken down into 3 control systems: pitch, roll, and yaw. The autopilot's maneuvering capabilities are classified according to the number of axes which it can control. A single-axis autopilot is aileron only. A double-axis autopilot is aileron and elevator, and the triple-axis autopilot has full control of the aircraft, aileron, elevator, and rudder. The Boeing 737-300 autopilot system has the following modes of operation, excluding autothrottle and speed modes: 1. Heading, 2. Lateral navigation, 3. VOR/localizer, 4. Altitude hold, 5. Vertical speed, 6. Level change, 7. Vertical navigation, 8. ILS. The flight director uses calculations by the autopilot system to display on the attitude instrument a desired pitch and roll in order to maintain the flight management computer flight path. If the AP is disengaged, the pilot can follow these command bars to fly the autopilot computed path. Autoland has triaxial autopilot and RNAV incorporations that allow for instrument approaches without pilot input whatsoever, all the way down to the rollout. Autoland may only use one computer, but can be duplex, triplex, or quadruplex, depending on the number of independent redundant autopilots and channels. These are known as fail operational systems. Auto brake systems allow for a continuous deceleration and automatic regulation of individual brake discs to produce the greatest braking efficiency. These systems typically have landing settings 1, 2, 3, and max, as well as an rejected takeoff setting. Modern aircraft use this system in conjunction with reverse thrusts where brake operation is less efficient, such as high speeds immediately after touchdown. Tire temperature before the takeoff run also depends on taxi time, aircraft weight, outside air temperature, and amount of braking used, because heat is transferred from the brakes to the tires themselves. Brake temperature must be below a certain limit before beginning the takeoff run to account for the possibility that the takeoff may be aborted before V1, ensuring the brakes will function properly and not exceed any limitations. With a crosswind during landing, the downwind brakes will become hottest because they compensate for the wind-induced yaw movement. The anti-skid system protects the wheels against locking during braking, skidding, or slipping. Hydroplaning is also protected by this system. It ensures 0% brake usage at the moment of touchdown to prevent or reduce the time before the wheels are up to speed when in contact with the ground. Cabin pressure is measured as a differential between the pressure outside the aircraft and within the cabin. It can be thought of a PSI value of the internal air mass pushing outwards on the fuselage, for example, 8.21 psi. Cabin pressurization is controlled by the outflow valve. It restricts outflow if the cabin pressure needs to be increased, and it liberates outflow if the cabin pressure needs to be decreased. Crossing 14,000 feet of cabin altitude, passengers should go on oxygen. Crossing 10,000 feet of cabin altitude, pilots should go on oxygen, and there must be oxygen for the entire flight time above 10,000 feet cabin pressure. In the worst possible scenario, for example, depressurization above high terrain. In the normal setting, the oxygen masks deliver sea level pressure oxygen mixed with cabin air. Since oxygen is 21% of the atmosphere and the sea level pressure is 14.7 psi, sea level oxygen is at around 3 psi. 100% oxygen can be delivered under two circumstances: demand and emergency. Demand shall be used for life support reasons to simulate a normal sea level quantity of O2. Emergency, for life support reasons above 34,000 feet, hypoxia, or cabin smoke. Emergency oxygen is not mixed with cabin air, is supplied pure and under pressure. Cockpit electrical fires should be contained using BCF fire extinguishers. Specific gravity is in kilograms per liter of a substance at a given temperature. It's important to remember that specific gravity changes with density, aka temperature, of the substance. 1 liter equals 3.78 US gallons or 4.54 imperial gallons. 1 kilogram is 2.2 pounds. Specifically, in larger aircraft, fuel is measured in weight rather than in volume. This is because these aircraft experience large temperature variations in which fuel expands and contracts, but always remains in the same weight. Cockpit windows are heated not only to prevent icing, but to keep them flexible and thus resistant to bird strikes. Electricity can be better understood through thinking of it as a system of water, where voltage is the water pressure and amperage is the flow rate. An area of high resistance can be thought of as one where the water pipe becomes thinner. A watt is a measure of electrical power. It is volts multiplied by amps. An aircraft should carry at least 3 fuses of each type used, or 10% of the total number of each type of fuse used, whichever is greater. Circuit breakers can be non-trip free or trip free, the former of which allows you to manually keep it pushed in during an overload condition as an emergency measure, even if that may damage the electrical system which the fuse is designed to protect. AC power is advantageous as it can be generated using alternators, which are simple in construction. AC systems are also lighter in their power-to-weight ratios. AC voltage can be converted efficiently using transformers. AC can easily be converted to DC if needed using a transformer rectifier unit. AC generators are also more reliable, especially at high altitudes. An inverter is a device that converts DC to AC. Transformers use magnetic induction between a primary and a secondary winding to increase or decrease the alternating current voltage. Engines normally drive a hydraulic pump, which in turn drives a hydraulic motor. This motor is a constant speed drive and maintains the alternator functioning within 5% of 400 MHz at all times. Constant speed drives can be disconnected from the engine at any time, but may be only reconnected on the ground with the engines switched off. End of chapter 6. Before we start the next chapter, I'd like to ask you to press the thumbs up button below the video player. This helps my videos to be recommended to more pilots so that I can reach a wider audience. Thank you for your support. Chapter 7. The ACE Technical Pilot book has not been updated to use terminology which is current for modern aviation authorities and syllabi. It uses things such as APS weight instead of dry operating mass and many other errors. Please pay attention to the following image instead of to the Technical Pilot interview book. Basic empty mass is the mass of the airplane plus standard items such as unusable fuel, fluids, engine oil, fire extinguishers, oxygen equipment, etc. Dry operating mass is the mass of the airplane ready for the operation, excluding usable fuel and traffic load. This includes things such as the crew, their baggage, as well as the catering. Traffic load is the total mass of passengers, baggage, and cargo, including any non-revenue load. Takeoff fuel is the fuel to be used from the beginning of the takeoff run until parking at the destination gate. It does not include start and taxi fuel. TORA is the usable length of the runway available for takeoff. Takeoff run available. TORR for all engines operating is the distance from the start of the takeoff roll until halfway between liftoff and the screen height multiplied by 1.15. TODA is the length of the usable runway plus the length of the clearway available, at the end of which the aircraft should be at V2 and screen height. TODR is the distance required for the aircraft to attain screen height at V2 factored by 1.15 times. The takeoff distance of an aircraft starts at brake release and ends when the aircraft crosses screen height. The landing distance is from screen height until when the aircraft has slowed down enough to exit the runway. Screen height varies by category. It is 50 feet for propeller driven in dry conditions, 35 feet for jet aircraft in dry conditions. Screen height is reduced when considering wet and/or engine failure conditions. ASDA equals TORA plus the stopway. It is the accelerate stop distance available. Emergency distance required is a distance until which the pilot will be able to accelerate to V1, have an engine failure, and still reject the takeoff on the ground without reverse thrust. This distance is then factored by 1.1 times for safety. A balanced field exists if the takeoff distance is equal to the accelerate stop distance. There is a call-out between 40 to 100 knots during the takeoff roll to ensure that the directional control has been attained, that takeoff engine pressure ratio has been set, and to cross-check the co-pilot and pilot airspeed readings. V1 is the speed in the event of an engine failure in the takeoff roll at which it is possible to attain screen height within normal takeoff distance available, as well as where it's possible to abort the takeoff within accelerate stop distance available, meaning below V1 the takeoff will be rejected, above V1 the takeoff will be continued regardless of engine failure. V1 is restricted at the low end by VMCG, which is the velocity of minimum ground control, and at the high end by VMBE, which is the maximum brake energy. If field length is limiting, a heavier aircraft will have a lower V1 to provide greater stopping distance. If field length is not limiting, the heavier aircraft will have a higher V1. If V1 is greater than calculated VMBE, the aircraft weight has to be reduced until V1 is lower than VMBE. VA is the maneuvering speed at which full elevator deflection first causes a stall to occur at the load limit factor. It is specified in the manual. VMCG and A varies with center of gravity positioning, as the yawing moment of the tailplane and arm of the asymmetrical thrust producing engine is dependent on this factor. Aft center of gravity requires a higher VMCG/A because of the reduced tailplane moment. VMCG must be less or equal to V1. VMCA must be less or equal to V2. If VMCG is limiting for the weight of the aircraft, reducing takeoff thrust causes a reduced asymmetrical moment in the engine failure scenario. Less thrust means less rudder input required to maintain directional control. V2, the takeoff safety speed, is achieved by or when crossing the screen height so that directional control and adequate climb performance is maintained in case of an engine failure. V2 cannot be less than 1.2 times Vs or 1.1 times VMCA. V3 is the all engines operating speed which will be achieved at screen height. V4 is the all engines operating climb speed to be achieved by 400 feet, the lowest point at which acceleration to flap retraction speed can be initiated. When calculating takeoff or landing performance, it's not recommended to use more than 50% of the reported headwind, and no less than 150% of the reported tailwind. The following is an extract from Wikipedia. The runway length required for an aircraft to take off is calculated for each flight. Depending on the aircraft weight, the air temperature, and the wind speed, this length may be shorter than the available runway length. The crew can calculate the low-power engine setting, where takeoff will use a larger portion of the runway. Lower power settings reduce noise, engine wear, and maintenance costs. This technique is based on air temperature rather than the percentage of engine power to be used, because it is easy for the crew to look up and calculate the highest air temperature at which any particular takeoff can be performed. That temperature is the highest flex temperature that can be used. Jet engines produce reduced thrust as the ambient air temperature increases. The flex temperature is the highest air temperature at which the engines would produce the required thrust. The crew finds that temperature and enters into the FMS, effectively telling the computer to assume that the specified air temperature, instead of the actual air temperature, is present. When the flex thrust is selected during takeoff, the engine controller produces maximum thrust for the assumed temperature. If necessary, the crew can push the throttles into the takeoff go-around detent and request full power from the engines. Reduced thrust takeoffs are not permitted if there's a contaminated runway, if the anti-skid is inoperative, if the reverse thrust is inoperative, if the aircraft is performing an increased V2 procedure, or if the PMC is off. Gross performance is achieved if the aircraft is maintained and flown according to the FCM. Net performance is gross performance diminished to account for variations in technique and reduced performance, so that the gross performance will be achieved 50% of the time. Departure profile segments are Segment 1, from the screen height until the landing gear is retracted and a constant V2 speed. Section 2, from when the Segment 1 ends until the acceleration height is achieved at V2. Segment 3 is the level flight acceleration segment during which the flaps are retracted. And Section 4 is from the end of Segment 3 until a height of 1,500 feet or more is achieved, with flaps up and max continuous thrust. An increased V2, also known as improved climb profile, is used if an aircraft needs to clear an object within the second segment. This procedure requires a greater takeoff distance or a reduced takeoff mass. Increased V2 procedures cannot be used when takeoff mass is field limited, because in this procedure, more runway is used in order to increase the takeoff speed. A reduced thrust takeoff will use more trip fuel, and the reduced thrust means that the aircraft will spend more time below its optimum fuel consumption altitude. Maximum endurance speed is that flown at the lowest point of the total drag curve, corresponding with the lowest specific fuel consumption. Maximum range speed is slightly greater than the maximum endurance, roughly 1.32 times VMD, because the drag curve is flat at the bottom. Airspeed can be significantly improved by 32%, while only resulting in a very small drag penalty. This increases range. Max range cruise is the maximum fuel mileage. Long range cruise is a significantly higher speed, which only results in a 1% mileage loss. Long range cruise speed should increase throughout the flight as fuel is burned off. Cost index is a number provided by the ops segment of the airline and is put into the FMC by the flight crew. It's a number that manages performance to ensure the lowest possible operating costs considering a multitude of factors, such as fuel price at the destination. Cost index 0 means the minimum fuel consumption and maximum range. Cost index 999 would result in the minimum time en route. A jet flight carried out below optimum altitude will burn more fuel, but it will take less time to complete when flying at constant Mach, because
because the local speed of sound is lower at higher altitudes. A set Mach number will correspond to a higher airspeed at lower altitudes. A step climb during cruise is performed because as fuel burns, the aircraft can fly at a higher, more efficient altitude. Critical point or equal time point is a point in which it would take the same amount of time to return home as it would to proceed to the destination. Distance to critical point equals the total trip distance times the ground speed home divided by ground speed out plus ground speed home. A headwind moves the critical point closer to the destination aerodrome, as it means the ground speed home would increase due to tailwind. PNR, or point of no return, are procedures generally used when you are committed to landing at your destination, for example, if your destination is a remote island. Landing distance available is that from the fence height, which is 50 feet above the threshold, until the end of the landing runway. Landing distance required is the required distance from crossing this fence until coming to a full stop. VMCL is the minimum air control speed in the landing configuration. VAT is the velocity at threshold. It is more often referred to as VREF and often corresponds to 1.3 times the VS. A pilot must ensure he crosses the threshold at this speed to guarantee the calculated landing performance for that field, especially if the runway is tight in length. As a guideline, 10% increase in weight means a 10% increase in landing distance. High humidity, and likewise low density, means an increased landing distance. Restricted landing weight is restricted due to runway length and conditions. It also considers engine out overshoot performance, weight, altitude, and temperature of the airfield.
End of chapter 7 and end of video. Thanks for watching.